In this last lecture on closed and open subsets of R, for the time being, we will be discussing the interaction between closed and open subsets of R and also the Bolzano Weierstrass theorem. So the first result is that if we take any subset of R, capital A say, then A is closed in R if and only if its complement AC is open in R. So let us try to prove this. Uh, First, we will notice that in two special cases, that is when A is equal to R, then A is closed and its complement is obviously the empty set which is open. Again, if A is the empty set, then it is a closed set and its complement is the whole of the real line which is an open set. So at least if A is equal to R or A is equal to empty set, then the result is clearly true that A is closed if and only if its complement is open. So we now take the non-trivial case, that is, suppose capital A is a non-empty proper subset of R, and suppose that it is a closed set. Then we will show that A complement is open, and then we have to show the converse also. So we have assumed that A is a closed set. So if you take any point in the complement of A, little x suppose, then x cannot be a limit point of A, because A is closed implies that the derived set of A is a subset of A. So x is not a limit point of A means that there is at least one delta neighborhood of x which will not intersect A. In your definition, you had A minus x, but since x is not in A, so A minus singleton x is the same as A. So therefore, since x is not a limit point of A, you get that the at least one delta neighborhood of x whose intersection with A is empty. But that means that this delta neighborhood of x is a subset of A complement. But that implies that this point x is actually an interior point of A complement. So you had started with any arbitrary point of A complement and you are showing that it is an interior point of A complement. Therefore, what you have proved is that A complement is a subset of interior of A complement. Hence, by definition, your A complement is an open subset of R. So one way you have proved. Now you have to show that if A complement is open, then A is a closed set. So you assume that A complement is open and take any x in A complement. Then x is clearly an interior point of A complement because it is an open set. So every point of the set is an interior point. So by definition of interior points, there is a delta neighborhood of x which will be a subset of A complement. So since this delta neighborhood of x is a subset of A complement, it means that the delta neighborhoods intersect of x, that's intersection with A, is going to be empty because it is totally a subset of A complement, so it is disjoint from A. So, but that means what? That you have found at least one delta neighborhood of x which does not intersect A at all. So that means that x is a limit pointer. X is not a limit point of A. X was what? X was an arbitrary point of A complement. You showed that that cannot be a limit point of A. So if anything is a limit point of A, it has to be an element of capital A. It cannot belong to A complement. So you get that the derived set of A is a subset of A, and that is the definition of a closed set. So A is a closed set. So it was quite a neat result, and if you compare your results which you have proved for open sets and closed sets, you will see that this result was being implied throughout, because in a sense, if you had used De Morgan's law, and if you use this result, then whatever you had proved for open sets could have been used to prove for closed sets also. Right? Remember what was your De Morgan's law? It was A, if you take any two sets A and B, so it can be any arbitrary many open sets also. So let me say it only for two sets. So if you take two sets capital A and capital B, then the complement of A union B is complement of A intersection complement of B, and the complement of A intersection B, that is A intersection B complement, is equal to the union of A complement and B complement. So this is your De Morgan's law, which is I'm stating for two sets, but it is actually true for arbitrary many sets. And therefore, if you use that law and if you use this fact that a set is open if and only if its complement is closed, then you will notice that you can give a separate set of proofs of all the results which you proved for closed sets using the results of open sets or vice versa. Okay, so the next result is slightly in a different vein, but this tells you what, that if you take any non-empty proper subset of R, then it can either be open or it will be closed, or it can be neither open nor closed, right? So we have seen many examples of open sets and closed sets. Let's just think about them. You saw that your empty set was both open and closed. Also, the set of real numbers is both open set and closed set. You also have examples of sets which are neither open nor closed. For example, the set of rational numbers is not neither open nor closed. So, and you just now proved something about a set being closed if and only if its complement is open. So you have all this knowledge in your mind. Now further, you want to extend your ideas to say that if you want a subset of R to be both open and closed, then it has to be either the empty set or the set of real numbers. So if you take a non-empty proper subset of R, it will not simultaneously be open and closed. It can happen that it is neither open nor closed. For example, the set of rational numbers. But if it satisfies either the properties of an open set, then it cannot satisfy the properties of closed set. And if it satisfies the properties of closed set, it cannot satisfy the property of open sets. So let us just try to prove this. So the proof is by contradiction. So whatever we want to prove, we assume that the negative of that statement is actually true and show that that will lead to a contradiction. So suppose, if possible, capital A is a non-empty proper subset of R which is both open and closed. So what does that mean? First of all, that if you look at A is a proper subset of R, so there is a point C which will be in A complement. So A will be a subset of open interval minus infinity to C union C to infinity. So you're leaving out C here. So just look at this particular diagram. It might help you that what I have tried to do is that I tried to draw the real line in a shade of gray, and the blue portions are the set capital A. And so some of it can lie on the left hand side of C, some of it can lie on the right hand side of C. And when C is not a point of A, so that I am clarifying by showing C as showing C in red. Okay, so A is non-empty, so it means either its intersection with this portion minus infinity to C will be non-empty, or its intersection with C to infinity will be non-empty, or it may intersect both the segments. So that is what we have written here. So let us see what will happen. First, let us look at this part, that suppose that A intersection open interval C to infinity is non-empty. So there is this portion of the set capital A here. There is some other little segment here which is also in capital A. There are some points which are not in A also. So the general situation will look something like this. Okay, so suppose that this is non-empty. Now what can you say about this set which is on the right hand side of C, that is a subset of C to infinity? C is going to be less than every number on the right of C, right? So if you take any point of capital B, then that is going to be strictly greater than C. So C is a lower bound of capital B. Therefore, B is bounded below by C. Obviously, we have assumed that it is non-empty. So B is a non-empty bounded below subset of R. So hence we know that its greatest lower bound will exist. So let us call the greatest lower bound of B, infimum of capital B, to be equal to little b. So it will be somewhere here. Since it is the infimum, that is, it is a lower bound, there will be no point of capital B on the left hand side of B, right? So that is what we have tried to show. And we don't know whether little b will belong to capital B or not at the moment. So for that, we are just using this open brackets, opening of the open bracket symbol here to show that B will be here. Okay, so B is the infimum of capital B. So first of all, C was a lower bound and B is the greatest lower bound. So B is greater than equal to C. Now there are two possibilities. B may belong to B or B may not belong to B. So if B belongs to B, first of all, then obviously B belongs to A, because what is B after all? B is the intersection of capital A with open interval C to infinity. So capital B is a subset of capital A. So if little b belongs to capital B, then little b has to belong to capital A, first of all. And suppose if possible, B does not belong to B, then what happens? Now, if you take any delta greater than 0, then little b is the greatest lower bound of capital B. So if you increase B by a delta amount, that is, if you look at B plus delta, then you will be able to get a point of capital B, which will be such that B little less than or equal to Y less than B plus delta. That is the definition of greatest lower bound. That is, if you increase the number by a quantity, then that will no longer be a lower bound. Hence, there will be a number of the set which will be less than that. That much is okay. And here we had in general B less than or equal to Y. But now in our case, we have assumed that B is not in capital B. So if Y belongs to capital B, automatically Y will be not equal to B. So we can clearly write that little b, I will be able to get a little y in capital B such that little b is less than y is less than B plus delta. So what does that tell you about Y? Y belongs to the open interval B minus delta to B plus delta. Also, Y belongs to B implies Y belongs to A, and also Y is not equal to B. So Y is actually in the intersection of the delta neighborhood, deleted delta neighborhood of B and A. So this you got for any delta greater than 0. So doing some simple uh, observations and concluding, we get that if we take any delta greater than 0, it will be possible to show that the deleted delta neighborhood of B will contain a point of capital A. So little b will be a limit point of capital A. Now, what had you assumed about capital A? Capital A was both open and closed, right? It is a non-empty proper subset of R and it is both open and closed. So, since it is at least closed and little b is a limit point of A, so B has to belong to A. So, whether B belongs to B or not, it doesn't matter. We get that B belongs to A. But now, in this particular case, you notice that C is not in A. So B belongs to A and C is not in A. That is what we had started with, right? So B is clearly greater than C. We knew that B was greater than equal to C because B was the greatest lower bound and C was the lower bound of the set capital B. But now we see that B belongs to A and we know that C does not belong to A. So B and C cannot be equal and hence B will be strictly greater than C. So what does that mean? That means that B belongs to the open interval C to infinity. So B belongs to the open interval C to, little b belongs to the open interval C to infinity. Little b also belongs to A. So in fact, little b belongs to capital B. This is okay. All right. So even if we were thinking that maybe little b will not belong to capital B, we see that by arguing logically, we get that little b actually has to be an element of B. So our picture is like this, that B is now in capital B. Forget about these things, I'll tell you what this is. So you had this C which is not in A. There is some portion of A maybe on the left of C. Right now we are not bothered with that. And you have B which is the greatest lower bound of capital B and which is an element of capital B. So you have this point here and from here onwards you have some portions of capital A sitting on the right of C. Okay. Now what can you say about little b? Little b is in capital B means little b is in capital A. And we had also assumed that capital A is an open set. So we should be able to get a delta neighborhood of B which is totally a subset of A. Right? So we should be able to get a B minus delta to B plus delta open set which is contained in A. The way I have drawn B minus delta to be greater than C, but that is not necessary. It may B minus delta could be somewhere here also. But whatever we are trying to say is that this B minus delta to B plus delta, this segment should actually belong to capital A, and that will lead to a contradiction you can see from the picture itself, because anything less than B and greater than C cannot belong to capital A. Capital A intersection open interval C to infinity, that means this portion was exactly equal to capital B and little b was the lower bound of that. So anything less than little b cannot be in capital B. But we are saying that something like open interval B minus delta to B plus delta is in capital A, but that will imply that there will be points which will be greater than C and less than B, which will belong to capital A. It is almost clear from our picture which we had drawn, but let us prove it rigorously. So what we do is we have two numbers. One is B minus C. B is greater than C, so B minus C is positive, and we have another delta, so that the delta neighborhood of B is a subset of A. Delta is also positive. Look at the minimum of these two positive numbers, that is a positive number. So you can choose a positive number D which is less than the minimum of delta and B minus C. So how is this going to help? Since D is less than delta, B minus delta will be less than B minus D, obviously, and B minus D is clearly less than B because D is greater than 0. Therefore, what did you get? You got that B minus D belongs to open interval B minus delta to B. That is a subset of the open interval B minus delta to B plus delta. Therefore, B minus D is actually a point of A, which we have depicted here by a star. Also, you have that D is less than B minus C. This implies that just by a simple manipulation, C is less than B minus D. So B minus D is in the open interval C to infinity. Therefore, B minus D belongs to capital A and B minus D belongs to open interval C to infinity, means it belongs to the intersection, that is B minus D belongs to capital B. But it is a contradiction because B minus D is a number which is strictly less than B, and B is the lower bound of capital B. So this is not possible. So you get a contradiction. So from where did you get a contradiction? You got a contradiction from the fact that you assumed that A intersection open interval C to infinity is non-empty. So this statement is false. So at least A intersection open interval C to infinity should be an empty set. So whatever portion of A lies, it should be in less than C. That is what we are trying to say. Let us see where it will lead us to. So we get what? That A intersection open interval minus infinity to C is non-empty, because A is a non-empty set. So it should either intersect this portion or the other one or both. But we have seen that A intersection C to infinity, this non-empty was leading to a contradiction. So this portion is going to be empty. So A intersection open interval C to infinity is an empty set. So we assume, so this other one has to be non-empty. So again, I have given the same name. It should not cause a problem. Let capital B will be equal to now capital A intersection open interval minus infinity to C. So you have this portion here, which is on the left of C. So what is happening about capital B now? Every element of capital B is less than C. So C is an upper bound of capital B. So B is a non-empty bounded above set, hence its supremum exists. So let us call the supremum little b again. Doesn't matter. Okay. So since little b is the supremum, it is the least upper bound, and little c is an upper bound. So b is going to be less than or equal to c. Again arguing as before, let us see if b belongs to capital B. Notice in this picture we have again used the end of the open interval thing here, first brackets right hand first bracket, to show that B may not belong to capital B. We will prove that B will actually belong to capital B. So how are we going to argue that? First of all, if B belongs to capital B, then B belongs to A. There is nothing to be said, because capital B is a subset of A. Suppose B does not belong to capital B. If it does not belong to capital B, now you use the fact that it is the least upper bound of capital B. So if you take any delta greater than 0, and if you decrease B by B minus delta, then this will no longer be an upper bound of capital B. Hence, there will be a point little y of capital B, so that B minus delta is less than y less than B. Again, less than because y belongs to B, and now B does not belong to capital B. So we will be able to get such a y. But that means what? That y belongs to open interval B minus delta to B, which is a subset of the delta neighborhood of B. So y belongs to the open interval B minus delta to B plus delta. Again, y belongs to B means y belongs to A, and y is not equal to B. So y belongs to A minus the singleton B. So you have got that the intersection of the deleted delta neighborhood of B with A is non-empty. So for any delta greater than 0, you have proved this. Hence B is a limit point of A. Now you have the fact that A is a closed set. So B has to belong to A. So B is always in A and C is not in A. So B has to be strictly less than C as before. So since B is strictly less than C, it means that B belongs to A intersection open interval minus infinity to C. Hence little b belongs to capital B. All right. So this will again lead to a contradiction. So little b belongs to capital B. So that we have now shown by putting a straight segment here. So B is in capital B now, right? But capital A is what? It is an open set. So I will be able to get a neighborhood, delta neighborhood of B, which will be a subset of A. From the picture you see that this is going to lead to a contradiction. However small your delta B, there will be some portion which is greater than B and which is less than C. So this portion should belong to capital B, and that is going to lead to a contradiction. And how do we rigorously write it down? Again, we are going to use same type of argument. So I have a delta neighborhood which is a subset of A because little b is an interior point of capital A. Capital A is an open set. So B belongs to A means B is an interior point of capital A. Very good. So you have a delta positive, and also you have this real number C minus B now, which is also positive. So if you look at the minimum of these two numbers, that is a positive number. So you will be able to get a positive number D, which is strictly less than the minimum of these two. So now what does that mean? We know that B is less than B plus D because D is positive. And B plus D is less than B plus delta because D is less than delta. So therefore, B plus D belongs to open interval B to B plus delta, which implies that it is an element of the open interval B minus delta to B plus delta, right? So therefore, B plus D is an element of capital A. Again, you have that D is less than C minus B. So B plus D is going to be less than C. So B plus D is also an element of the open interval minus infinity to C. Therefore, B plus D is an element of capital A intersection minus infinity to C. And that was what capital B was. So B plus D belongs to B. Now this is a contradiction because capital B was the upper bound, least upper bound of capital B. But B plus D is a number which is strictly greater than B, and it has to belong to capital B. So this is a contradiction. So from where are we getting this contradiction? By our assumption that A intersection open interval minus infinity to C is non-empty. So that is also false. So A intersection open interval minus infinity to C should be an empty set. But then what can you say about A? A does not intersect C to open interval C to infinity. It also does not intersect minus infinity to C. So that means that A has to be the empty set. C is not an element of A, we have already assumed. So A has to be an empty set. But this is a contradiction to our basic assumption from where we had started, that capital A is a non-empty proper subset of R, which is both open and closed. So this statement is false. So therefore, the statement that if you have a subset of R which is both open and closed, then it has to be either the empty set or the set of real numbers. This statement is true. Therefore, this theorem is true. I hope this is clear. Okay. Next result which we prove is Bolzano Weierstrass theorem. This can be proved in several ways, but it is quite illuminating to see that it can be proved without knowing anything more about real numbers. That is, you don't really need nested interval theorem and things like that. But since you are not going to use any sophisticated results, which you will prove later on, this proof will become slightly complicated. Expected because we have less knowledge, and from there we are trying to deduce this result. So it requires more of hard work, and when later on we use nested interval theorem, then you will see that things become simpler. So what is our result? The results is that if you take an infinite bounded subset of R, then it will always have a limit point in R. So we have seen several examples of infinite subsets of R which do not have a limit point. For example, the set of integers. You have also seen many examples of bounded, at least one example of bounded subset of R which does not have a limit point, that is the finite set. A finite set is a bounded set, it does not have a limit point. So if you leave out any of these two restrictions on the set, then you may not have a limit point. But if you put them together, that is, if you want a subset to be infinite as well as a bounded set, then it is bound to have, it is necessary that it will have a limit point in the set of real numbers. This is what we will prove. The proof is by construction. So let us see. Suppose I take an infinite bounded subset of R, capital S, and I construct a new set, capital H, which consists of all those real numbers which are greater than infinitely many points of S. Okay. So then look at, since S is a bounded set, its supremum as well as infimum exists in R. So look at supremum of S. Supremum of S is greater than or equal to every point of S, but it can be equal to at most one point of S, and S has infinitely many points. So supremum of S will be greater than infinitely many points of S, right? Even if supremum S is equal to some point in S, that will be one singleton thing. Apart from that, there will be infinitely many points. So supremum S is going to be greater than infinitely many points of S, and hence supremum S belongs to H. So that means that H is non-empty. Next, you notice that if you take any y, which real number, which is less than or equal to infimum S, then what can you say? Infimum S is the greatest lower bound. So it is less than or equal to every element of S. So if y is less than or equal to infimum of S, then y is also going to be less than or equal to A for all A belonging to S. So clearly y cannot belong to H. So if you take any point less than or equal to infimum S, then it cannot belong to H. So what does that mean? That if there is an element of H, it has to be greater than infimum S, right? Anything less than or equal to infimum S is not in capital H. So anything in H has to be greater than infimum S. So that means infimum S is a lower bound of H. So H is a non-empty bounded below subset of R. So infimum of H will exist. Okay. So let us call that infimum little x. We will show that little x is a limit point of capital S. How will we show this? We will take any delta positive. Then what can you say about x minus delta? X is a lower bound of capital H. So anything less than that cannot be an element of H. So x minus delta does not belong to H. What is the defining property of H? It consists of all elements of all those real numbers which are greater than infinitely many points of S. So if some number does not belong to H, then it cannot be greater than infinitely many points of S. So that means it can be greater than at most finitely many points of S, right? It, this is okay. Since it cannot be greater than infinitely many points of S, x minus delta has to be greater than at most finitely many points of S. So if in the picture on the left hand side of x minus delta, you will have at most finitely many points of S. Very good. Next, so what does that mean? S is an infinite set. So of that infinitely many elements of S, there are at most finitely many elements of S which are less than uh, delta, x minus delta, right? So infinitely many points of S are greater than x minus delta. This is okay. Now you look at x again. It is also not only a lower bound, it is the infimum of H. So if you look at x plus delta is an increment in x. So x plus delta is no longer going to be a lower bound of capital H. So we will be able to find a little y in capital H such that x is less than or equal to y is less than x plus delta. So y is in H means what? By the definition of H, y is greater than infinitely many points of S. So since y is greater than infinitely many points of S, x plus delta will also be greater than infinitely many points of S. So see, what are you getting? You have this x minus delta here and x plus delta here, right? So this open interval x minus delta to x plus delta. Infinitely many points of S are greater than x minus delta, and infinitely many points of S are less than x plus delta. Since x plus delta is greater than, so infinitely many points of S is less than x plus delta. So in the interval x minus delta to x plus delta, there will be infinitely many points of S. What was delta? Delta was an arbitrary, where is my delta? Delta was an arbitrary positive number. And we showed that the delta neighborhood of X will contain infinitely many points of S. So by what we had proved in the last lecture, we see that this implies that X is a limit point of S. So you have actually constructed a limit point. It doesn't mean that this limit point is unique. All you are saying is there will be a limit point of S provided S is a non-empty bounded subset of R. This is a very crucial result which is called Bolzano Weierstrass theorem. We will encounter this theorem later on again. Okay, the last result is just a exercise actually, but I thought maybe I will do it because it uses the terms countability and so on, and that scares a little bit at first reading, but it is not difficult, you will see. So our exercise is, or the proposition is, that suppose I take an infinite subset of R so that every point of E is an isolated point. Then we can show that E has to be countable. Okay, so how will we show that? Take any point in E, it is an infinite set, and you take any point X in E. Then X is an isolated point. So that means you will be able to get a neighborhood of X which will not contain any point of E other than X. X is an isolated point, means X is not a limit point. So there will be a neighborhood of X which will contain no other point of capital E except for X. So as we have discussed before, a neighborhood means it of any point means it contains an open interval centered at X. So we are not bothering about centering at X. We have just said there is an open interval. I could have written X minus delta X, X plus delta X, but that would look ugly. So I have not bothered about that. I have just said that there is an open interval AX, BX, so that AX, open interval AX, BX intersection E is exactly equal to singleton X. This is because X is an isolated point. Okay, now what you do is, so you have AX less than X less than BX. So you choose a rational number Rx between AX and X, and choose another rational number Sx between X and BX. Then what do you get? Rx Sx is also an open interval, and X obviously belongs to that, and Rx Sx intersection E is going to be also singleton X, because R open interval Rx Sx is a subset of open interval Ax Bx. So this intersection is singleton X, means this intersection can be only singleton X. Since X is there, so it could have been empty, but since X is there, and that is the way we have chosen these Rx and Sx, so this intersection is just a singleton. Okay, very good. So this we do for every point of E. Now look at script U, which is the collection of all open intervals having rational endpoints. In a lecture on countable and uncountable sets, I had shown that U is a countable family or countable collection. All open intervals having rational endpoints. Okay. Now you look at V, which consists of all these Rxsx, which you had chosen depending on little x belonging to E. So what is this? These are all open intervals with rational endpoints and some special types of such open intervals chosen depending on x belonging to E. So obviously V is a subcollection of U. U was the collection of all open intervals of sub R having rational endpoints, and V is all open intervals Rx Sx where x belongs to E. So Rx Sx are rational numbers. So that means V is a subset of U. So that means V is a subcollection of U. Now we know that any subset of a countable set is countable. So V is also countable. Okay. Now what can you do is you can write E as the union of Rx Sx intersection E, because this is just singleton x where x belongs to E. So you can always write it like this, where your Rx Sx belongs to this script V. So what does that mean? That the union you are taking is over a countable family. So it is a countable union, and each of this is just a singleton. So it is a countable set. So capital E is a countable union of countable sets, and therefore it is countable. I think this is okay. So we will stop here, and in the next lecture we will try to start about sequences of R.